Hello, everyone. Thanks for joining today. I'm Ben Dilday, representing Bloomberg today. Um, with my colleague Gatsby, we're both on the enterprise data lake team at Bloomberg, and we're going to tell you about building a historical data archive using Apache Iceberg. Next slide. Okay, so Bloomberg is a primary provider of financial data. Bloomberg's in the somewhat unique position of being a data provider for more than 40 years. And over that time, the main product from Bloomberg and the main way that users would interact with data is the Bloomberg terminal, which is shown here in the screenshot. The Bloomberg terminal is a really comprehensive piece of software. So it allows users to do in-depth analysis of individual securities, to do statistical analysis of sets of securities, to get access to Bloomberg models, get access to news, analysis. And the users of Bloomberg terminals are largely financial professionals and regulators. And it's important to understand for the purpose of this talk that the Bloomberg terminal is basically sold on a per user basis. Next slide. So we also have clients that are interested in getting access to the data, the raw data that backs the Bloomberg terminal. So the users here tend more to be organizations or what we call enterprises. So this is where the enterprise data in the enterprise data lake team comes in. So these are basically users that want to be able to build machine learning models, predictive models, basically do testing of their investment ideas. Yeah, next slide. So in this talk, we're going to go through two case studies. So the first, I'll talk about how we migrated from a collection of text files to a system where we use Apache Iceberg. And then Gatsby will tell us about how we apply enrichments to our data using the branching and cherry picking features of Iceberg. Next slide. So let me start by saying where we were before the enterprise data lake team began. So we had this large archive of data on the order of petabytes, and we stored it in basically text files. And the format of those files is shown on the left here. So it's essentially a CSV file with a header. And it's important to note that this data is actually typed data. So except that the types were stored in this external database that's maintained by Bloomberg as opposed to within the file itself. And so for a user to make use of this data, their workflow would be to read the data, parse the header to understand, okay, which fields are contained within this file, and then consult the external database to understand, okay, what's the data type of these fields and how should I be interpreting these text values that I'm finding. So the formatting in this external database can be pretty complex, but just for the sake of illustration, let me walk through a simple, a rather basic example. So the file might have a field called company ID, and then the user would look in the database to understand that this should be interpreted as a string. So as opposed to if you have just a 1, 2, 3, 4, 5, some long sequence of numbers, automatic parser might think that's a long integer or a double or something. On the other hand, there might be a field called price, and the database says this should be interpreted as a double, and so the user can understand that. And so, as I mentioned, Bloomberg has been a data provider for more than 40 years. So this system made a lot of sense at the time that it was implemented. It was a really good solution for providing typed data to clients. But our goal is to improve upon this process, and that's where the data lake part of enterprise data lake team comes in. Next slide, please. So when we began this project, we basically laid out a set of requirements that we wanted to satisfy. So first of all, we need to handle big data. As I mentioned, the archive is on the order of petabytes. We wanted to have strongly typed data. Although the data is typed, as I've just described, we want to more strictly enforce that and enforce that at the file level. We want to be able to incorporate republishing data sets, and the partition rights feature of Iceberg has been really helpful for us there. And we want to be able to handle schema evolution. So over the course of 40 years, it's inevitable that the schema of these data will change. We want to be able to handle that in to handle those evolutions. We have a very strong, very strong mandate that we must be sort of backward compatible for all of our historical clients. So all of these features are things that Iceberg really excels at, and led us to consider Iceberg. And then additionally, some things that are very strong points in Iceberg's favor are the ability to have snapshot history, do time travel within the tables, and the fact that Iceberg supports multiple client APIs. So in the tables I'm going to describe, there's two sets of users. The first are data analysts. So these are the financial professionals I described earlier, folks that are really interested in the data itself and using it to build their predictive models. The other one is the QC and support teams here at Bloomberg. So these are internal teams to Bloomberg. And it turns out that Iceberg has been really, really valuable for these folks. So I'll describe that as we go forward. Next slide. When we do our data ingestions, there's basically three modes that we operate in. So the first is onboarding and backfills. So onboarding describes the situation where we have only just begun supporting a data set. And so we have this archive of data that we need to ingest basically all in one go. Our requirements for this, backfills is a similar process, but that refers to the case where we want to make enhancements or corrections to data that we've already ingested. And this will be the topic of Gautami's portion of this presentation. Okay, so the requirements we have for onboarding and backfilling are that we want to be able to schedule these on demand. And we don't want to just operate on one date or one data set. We want to be able to operate on a range of dates. And it has to be resilient to schema changes and conversion failures. So basically, we're ingesting a large amount of data. We don't want it to fail right at the end for some reason, for a corrupted text file, let's say. And then we have to go back and do the whole process over. And because we're doing the entire archive in one shot here, the data we're ingesting is on the order of gigabytes or even terabytes. So then we have a mode of ongoing. So once we've ingested this archive of data, these data are generally being published, still. And so financial data is pretty generally published in once a day snapshots. And so we want to be able to ingest these snapshots into our archive. So for this process, we want this to be event driven. So basically we get a notification from our collaborating teams that a new data set is ready, and we need to be able to respond to that and ingest it into our tables quickly. We want this to be as near to real time as we can. Because we're operating on essentially one date at a time here, the size is more like megabytes or gigabytes in a few cases. And finally, we have our support tables. And these have different, basically, requirements for them. And what we need to be able to handle the sorts of queries that we expect our support analysts to be making. And so they have to be optimized for those queries. Next slide. So the architecture that we found works well for us is the following. So we either start our process in an ongoing for the ongoing process or for the onboarding or backfilling. For onboarding and backfilling, as I mentioned, we start that manually. For ongoing, we have a Kafka topic that we share with our collaborating teams. So we get basically a notification that new data is ready, and we can start our ingestion process. In either case, the text files that we start with are stored on S3 file system, compatible file system. And then our compute engine is Apache Spark. This has been really crucial for especially for the archiving, where we're processing so much data all at once. And we have a custom data source parser that we've written in Scala. This is important because in the financial world, there's a number of sort of financial specific formats that we expect to encounter. as an example, price open, like this, market open of a price of a security. It might be stored in this format of +3, superscript 176, subscript 256 to denote a fraction, and then M for million. And we need you to be able to parse values like this to understand what they mean. So then using Spark API, we write these data into our Iceberg tables. We're using the JDBC catalog for this use case. And then finally, our data, the backend, the backend for our data is, again, S3 file system and Parquet files. Next slide. So a very important design consideration for Iceberg is how you're going to partition your tables. So for us, for this use case, we partition by date. So as I mentioned, financial data is largely published on a daily basis. And so for us, this makes the writing, it's well optimized to write new data as it comes in. The trade-off here is that if somebody would like to do a query across the tables, let's say focus on an individual security and ask a question about, let's say the price, opening price or something across time, then this partitioning strategy isn't well optimized for that use case. But this is a trade-off that we make for these archived data sets. Next slide. Okay, so to contrast that for our support tables, so these tables support users, our Bloomberg support team that fields questions from clients and then uses these to give insights to the clients. So as an example, a client might come to the support team and say, I know Bloomberg publishes information about, opening price of securities or dividend yield or something along those lines. Can you tell me all the data sets that have this field? Another example might be a client will say, I got the latest publication for my data set that I'm interested in, and I found there's a whole bunch of null values in there. I wasn't expecting to see those. Can you help me understand what happened? And so to support these use cases, we have a couple tables. The first is fields. So in contrast to the data where we partition by date, for this one, we really need to support those queries. And so the partition strategy is a combination of data set and field names. On the other hand, for nulls, again, we partition by data set and field names so that we can answer those queries effectively. And in terms of the nulls, so this comes back to what I mentioned earlier about having to be resilient to conversion failures. So what happens when we find a value that doesn't make sense for the data type that we're expecting, rather than raising an exception or something, or just simply nulling out the value silently, what we do is we null out the value, then we add a column to our data set to collect examples of things that have been nulled out. And so this provides the ability to do queries to find out what went wrong with a particular data set. So an example shown here, dividend date is something we expect to be a date. But in this large archive of text files, we'll occasionally find values that don't make sense as a date, for example, 5. And so because we're unable to interpret that as a date, as I mentioned, we flag it as a null, put it in the table. And so then when a client comes to ask what happened with dividend date for this data set, our analysts can very quickly provide an answer to the clients. All right, next slide. The way we provide this data to end users is a couple different ways. So one is SQL. We have a Trino cluster sitting on top of our tables. And this is the primary way that the support teams interact with the data. Next slide. So finally, we also provide data to our financial clients in the format of Parquet files. And generally, we aggregate these on a daily, weekly, or monthly cadence. And the way we decide which one makes sense for a particular data set is we use the partitions metadata table. And one field they have is the total size of the file. And so we can aggregate this over daily, weekly, or monthly intervals to make an informed decision of what would make sense for this data. So basically, the data set's very large. We try to aggregate it as a weekly deliverable for a client. It might be too large for them to download reasonably. And so we use daily in that case. And so basically, this is just an example of how the metadata support within Iceberg has been really helpful for us. Next slide. Okay, so just to summarize, I explained how we began with petabytes worth of data stored in text files that were all stored independently and disjoint from one another. And now we've moved to a system where we have Iceberg tables, with strongly typed data, and we've found really great support for our support teams. So with that, I'll hand it over to Gautami.
Thanks, Ben. Thanks for the insights on how we build this data lake. Now, for the next case study, let's look at a scenario that we have encountered after building our data lake called the historical data enrichments, and how we leverage some cool Iceberg features to solve this problem efficiently. So what are historical data enrichments? So in our use case, so it's like filling in some missing data from a few years ago in our existing Iceberg tables. So the scenario here is that we have these tens of thousands of data sets with decades worth of data, which are already ingested into Iceberg in our production systems. That means all of these Iceberg tables have been QC'd and they are already client facing. And now we have identified a data gap in our historical records, and now we want to fulfill that. And how Iceberg has been really helpful for this use case is we leverage the branching feature, which helped us create an isolated testing environment. And by using the cherry pick operation, which is metadata only, to publish these changes from our audit branch, the main branch, we were able to do this historical data enrichments in a fast, safe, and efficient manner. So before I talk about how we actually did that, let's look at our underlying data model here. So what you see here is an oversimplification of our actual data model, but each row seems to represent a security at some point in time, and there is also some additional data associated with it. Our data sets look similar to this, right? So they have a group of fields, they span across a universe of financial instruments, and they are released at a given cadence. An example could be North American equities data set is published every day at NYC market close. A refresher on how we ingest these data sets into Iceberg, as Ben has already mentioned, we have this pipeline where we use Spark to ingest into Iceberg, and we have all these date partition tables. So we partition our tables by the date on which they are published. And this is our S3 object store here, where you could see these date partitions and the underlying Parquet data files underneath them. Okay, so more context on what are we trying to enrich. So there is an identifier called FIGI ID. FIGI stands for Financial Instrument Global Identifier. So it's a unique identifier to represent financial securities across time. So Bloomberg has introduced this open standard called FIGI in 2010. And I'm sure folks in finance would resonate with the fact that how we have all these security identifiers across different countries, different exchanges. And this problem is only worsened when companies issue corporate actions, say Facebook changing its name to Meta, and now all these identifiers change over time. So it was important to have an identifier like a primary key, so it could uniquely identify all these securities across time. But the catch was that FIGI was only introduced in 2010. So for all those data sets that we already ingested in Iceberg, all those date partitions before 2010 have null values for the FIGI ID. So in a finished state, we want to have filled in values for this FIGI for all those date partitions before 2010. And how can we actually do that? We can have a mapping table that has the actual values for the FIGI ID, and we join this with our Iceberg tables and get the coalesced value for FIGI ID. Okay, so how do we do this? The most brute force, crude way of doing this could be rereading all those input text files, the CSV files that Ben showed you, and then apply our enrichment logic on top, and then ingest all of this into Iceberg. Right, in production, we could do this in a lower environment like beta. So we could QC all of these changes, But the problem is that our input raw files have petabytes of data. That means we are rereading and re-ingesting terabytes worth of data. And then we are also QCing all of the data and not just the date partitions that were changed by the enrichment logic. So this is expensive and time consuming. So what we essentially wanted to achieve here was a fast, safe, efficient operation to manage these changes to these date partitions. So how do we achieve this with branching? Let's assume there is an iceberg table for a data set called equity NAMR. It's a North American equities data set that's published daily, and we have all these daily snapshot ingestions into iceberg. So let's say as of Jan 4th snapshot, we create an audit branch. And how do we create a branch? Is by issuing this alter table statement to create a branch. And once we do that, we also have to enable this walk property to true. This then enables the table for write audit publish pattern. And we also have to set the WARP branch to the audit branch that we just created so that all the subsequent writes happen to this audit branch without disturbing the main iceberg stable state. Okay, so we have created the audit branch. Now we could do a dynamic partition overrides to perform those data enrichments to fill in the Figgy ID before 2010. So in an ideal state, after we perform those data enrichments in the audit branch, we should have fill-in values for the Figgy ID for all those date partitions before 2010. So let's look at how the iceberg internal state looks like when we create a branch, right? So before that, let's say we created a new table and appended some data to it. Let's look at the snapshots metadata table. Once we append some data, we have a new snapshot and the operation is append. Looks good. Now let's create a new branch and see what the refs metadata table looks like. So we create a new branch. We also enable this walk property to true. And we see a new snapshot ID being created for the audit branch. This is inferred from the main branch's snapshot ID because we just created audit branch from main. Now let's look at both these metadata tables after we ingest some data into the audit branch. So before we ingest, we should remember to set this WARP branch to audit branch, and then we insert some data into it. So that means we should be able to see a new snapshot ID as seen here. And we should also be able to confirm that this snapshot ID in Iceberg corresponds to the audit branch in the refs table. So, and we could see that. So this is how you could confirm if all your writes are happening on your audit branch so that you're sure that whatever you're planning to do in your audit branch happens in the audit branch without disturbing the main Iceberg table state. Okay, so we have created an audit branch. We have done those dynamic partition overrides, performed all the data enrichments. Let's say we have already audited those. We have already QC'd those. Now, how do we publish those changes from the audit branch into the main branch? What we essentially needed was like a git merge operation because our data sets are published daily. So our main branch is getting updated daily, irrespective of what we do in our audit branch. So we needed something like a git merge where we could pick all the changes in our audit branch and like take it onto the main and apply it onto the main branch. So Iceberg doesn't have a merge operation, but it has a cherry pick operation, which is also conceptually similar to git cherry pick. So let's say you have the main branch with this commit history A, B, C, D, and then you have a feature branch with the commit history E, F, and G. And let's say you want to cherry pick a commit F from feature to the main branch. So what we are trying to do is take all those changes as part of the commit F and then apply it onto the main branch. And that is how Iceberg cherry pick operation also conceptually works. Let me just demonstrate that in the next workflow. So let's say we have an Iceberg table for a data set. We have all these daily snapshot ingestions. And let's say as of Jan 4th snapshot, we create an audit branch. We have done those data enrichments that we need here. Like I mentioned, our main branch consistently has daily ingestions. So by the time we QC our stuff on the audit branch, our main branch is growing, right? And how do we perform the cherry pick? So you can perform the cherry pick by calling this procedure called cherry pick snapshot and then providing the snapshot ID of the audit branch snapshot ID that gets created after you perform your data enrichments. So once you cherry pick, a new snapshot is created with the new metadata that will also include all the data files that have been either added or modified as part of your data enrichment operation. So cherry pick essentially is metadata only, hence it's fast, it's effective because it's metadata only, and it's safe here because we audited our audit branch and we are not disturbing or causing any disruptions to any of these partitions on the main branch. So that's how we were able to bridge the data gaps seamlessly using cherry pick operation. So I think to wrap it up, that's how we have built this historical data lake, and that's how we bridged our data gaps seamlessly using Iceberg in production. Moving on, future work. So I think before I talk about what lies ahead, I need to talk about where we all started it from. So when we first started using Iceberg, Spark and Java had this mature right implementation. We got started with it, and we started using in the process, we started using Spark and Java in all those places, even where we didn't need it. But we did it because we wanted to interact with Iceberg. And then Trino had this good read support using the Trino-Iceberg connector, and everything worked well. I think looking ahead, we are definitely exploring new horizons and very excited to embrace PyIceberg wherever it's the right fit. Our team has been making contributions to the PyIceberg community. Here are some of the contributions we have made. And we're definitely looking at optimizing some stuff, shifting gears from low latency way of doing things wherever applicable. An example could be for our ongoing ingestions, right? For the daily ingestions for our data sets, we don't have to launch a gigantic Spark cluster. Instead, we could leverage PyIceberg API to ingest those into Iceberg. And thank you for joining us today. I think before I conclude, a huge shout out to everyone who has contributed as part of this journey. And I know that was a lot to cover, but feel free to reach out to us at the contacts we have here. That's it. Thank you. Thank you for joining today.
Okay, well, thank you very much. We'll get to some Q&A here. Again, reminder, if you would like to ask a question for our presenters, you can use the Q&A feature in the browser, or if you want to ask on camera, just request to share your video and I will call on you to ask questions directly. But we have a number of great questions already in the Q&A section. So I'm going to pick a few of these here. The first one was about the usage of Spark in this pipeline. And it was really, most of your examples showed Spark SQL code, but are you primarily using Spark SQL, or are you using the data frame APIs, or some combination of those two things?
Yeah, we use both. We started with SQL, and now that the data frame API is also having regular updates and it's changing, we also leverage both. Yeah.
Yeah, makes sense. There's a number of questions here which are related, so I'll kind of group them together. And it was about your partitioning strategy in particular. You mentioned using dates. It looked like there was already a date as a column in the source data, so you weren't using sort of Iceberg's transforms, like date transforms partitioning. Maybe you can speak to that. But also, did you try any other partitioning strategies, either on like Figgy ID or Ticker, or a bucket of that, or using any other clustering techniques for query performance that are interesting to share?
So I think the partitioning strategy that we use for our main tables is by the date on which our data sets are published. That was the ideal way for us because we wanted to optimize for our writes. And for our support tables, like Ben was mentioning, we use a combination of bucket partitioning with the field name and data set, because those are for our support users who query those tables, and they either filter using the field names or the data set, and that made more sense for us to have a combination of bucket partitioning along with the field or data set associated.
Great. Another question here about cherry picking. Can you just maybe talk to the specifics? You know, when you cherry pick something into Iceberg, what is actually happening? Is there a chance for conflicts? How do you resolve those if they happen?
Sure. So cherry pick definitely has some caveats, I would say. So when you try to cherry pick a snapshot ID from audit branch onto main, you need to make sure that the parent of the audit branch's snapshot ID is an ancestor of the current table state. That's one thing. And also, I mentioned that we are only doing this for historical data enrichments. So if on the main branch, if the same partitions change that are being also changed in the audit branch, it wouldn't work, because then Iceberg would detect there's a conflict, it would error out. But in our case, we only deal with historical data enrichments. So this is kind of a very rare edge case. Let's say when a data set that has been, there is a republication for a data set from 2006, which like very, very, very rarely happens. So it's like a rare case that we know would happen, but ideally it's just for historical data. So our cherry pick would work as expected.
Makes sense. Okay, I'm going to go to some live questions here. I think we have Pauline. I'm going to let you in for your question. Are you able to join? Maybe. All right, well, we're working on that. There was a question about, do you use the time travel feature of Iceberg? And if so, is it easy to use in terms of queries? Is it efficient? How's your experience been if you have, or if your users are using the time travel features at all?
So we use time travel sometimes. I think we are just starting to introduce it in some of our production use cases. Haven't observed any performance issues related to it. So it all ties down to if you perform some maintenance operations on your Iceberg tables, your time travel gets affected. But right now, our main tables in Iceberg, we don't have maintenance operations set upon them, because essentially we do a dynamic partition override. So we replace the partitions. So there's not much Iceberg metadata growing there rapidly. So we do have some use cases, but we haven't observed any specific issues with respect to it. And it was very easy to use. We even use time travel with like our Trino and stuff. So the API has good SQL support and stuff like that.
Fantastic. Shifting gears a little bit, these next couple of questions are kind of about some kind of scale questions. The first one is about the ingestion. You mentioned, there's backfill, but there's also ongoing ingestion. What's the scale of sort of like the daily ingestion? And are you doing that in batch, or is that sort of some sort of record by record or CDC?
Let's see. So the scale, like kind of top of my head, we ingest about 10,000 data sets a day, and average, I would say 100 megabytes per data set. So it's a million megabytes, I suppose. Is that correct? And I'm really interested in the question about real time versus batching. We do it in batching, and that's largely because the data we're working with come to us in batches. So like it will be, for example, at market close, we'll get a summary of the trading for the day. That's really mainly the data that we're dealing with. So we have experimented recently with using Flink for streaming data. And we started with the use case of the support tables. So that's something that we have looked at. And I think sort of, how that's going to finally be worked into our system is still up in the air. Let's see, there was... sorry, did that answer the question, or was there something else?
No, I think that's great.
Okay.
I think that's great. Since we're on the topic of ingestion, you have to a little bit about handling some of maybe the data quality issues, but if you have stuff that is not schematized or doesn't fit into the schema at all, do you have a situation, how do you handle those records? Do you have some sort of like dead letter queue or dead letter table for this data to land in for future inspection or quality control purposes?
So we've really had an iterative process here. So we sort of began by being a little bit pretty agnostic about what we expect the schema to be, and just ingesting them, kind of seeing what's there. We've worked with other teams there at Bloomberg whose mandate is to kind of be the source of truth of this data typing and metadata with Bloomberg. And so they provide schema to us, which we use to ingest the data. And so basically, if we encounter a problem, we switch back to this other mode where we can ingest it all as basically strings and do some more in-depth analysis of why did the schema not match. Then we report back to the other teams and we kind of go into iterative process. So mainly we are ingesting like schematized data, but that's our process if something doesn't match. So we don't have like a dead letter kind of table. But we do kind of flag conversion failures, like I mentioned, and keep track of those. Yeah,
that's a never-ending problem, I imagine. A question here, a couple of folks related to the write audit publish pattern that you described for doing these, fixing corrective actions on historical data. You were setting some properties in the Spark session, and the question really is: are those Spark session scoped properties? Are they scoped to particular tables? How do you control that, or do you think about that?
Yeah, there's Spark specific properties. You need to set them on the writer to be able to enable your audit publish pattern and also make sure your subsequent operations happen on the audit branch. Yeah.
And I think those are session level properties in Spark, right? So they would apply potentially to any table you might be writing to if you have writing multiple tables in the same session. Yes. Okay, we do have a live question. Oh, come and gone. If you want to come back and ask your question, please go. Feel free to do so. It looks like the poll is also open. So again, we'll have a few more questions here until the top of the hour. But if you're here, please do fill out the poll. It's a fantastic session by Ben and Gautami. We appreciate that. Let them know your thoughts. Here's a new question. Are you using clean rooms, the notion of clean rooms, to publish data, Bloomberg data to your customers, without actually, through some sort of sharing mechanism versus like moving files or copying data files? Anything you can share related to how you're doing that?
So I'd say that yes, we are experimenting with that, but that's really outside of the kind of area of expertise of our team. So that's about all I can really say about that. Yeah.
Okay. All right. Maybe future work. Interesting area of exploration. Couple of questions related to the Trino use cases. Have you had any performance issues, memory pressure for large queries in Trino in particular? And then maybe generally, why Trino as the query engine of choice here?
So yes, we definitely have memory issues with Trino. It really depends what query someone does, and because we expose it as a fairly open entry point into the data for a very large set of people, users at Bloomberg. It can definitely happen, and it definitely does happen. And basically, we are running the Trino cluster, and so we periodically have to go and investigate, possibly halt queries that are taking too much time and things of that nature. So yeah, it definitely happens. And I think we've sort of we sort of got a culture where people are generally aware of this, and so that it tends to kind of happen less and less as people understand those constraints. And I think another thing is that the SQL interface is mostly used for a little bit of exploratory work. It's not really the primary entry point into like large amounts of financial data to do model building and things of that nature. So that also kind of limits how much we see that. And in terms of why Trino as opposed to something else, I'm afraid that like predates my my membership on the team. I really don't have any great insights into that. Sorry.
That's okay. That's a fair answer. There's a few questions here related to the catalog, the Iceberg catalog that you all are using. I think you mentioned it's the JDBC catalog. Any experience you can share there, like why JDBC, if anyone was there for that decision, or things that are maybe worked well or challenges you faced in using the JDBC catalog?
Yeah. So I'm sorry to say. Also, that predates my membership on the team. But what I can say is that as got to me touched on, we're really trying to move to REST catalog for many more things. So that's the direction we're thinking that we're basically trying to head going forward. But in terms of historically, why JDBC? I mean, one thing is Bloomberg just has really good support for JDBC tables. So I mean, I'm afraid I don't have any like better answers than that.
All right, that's right. We're just almost at time here. We're going to get kicked out, I think. But I'm thinking the last question, which would be, what impact do you think in terms of your user base and usage of this system while having a full featured like Python client for Iceberg tables? You talked about some of the PyIceberg work that's going on. What impact do you think that will ultimately have for you and your users?
I can take this. Impact for our users will be the same, because instead of leveraging Spark for some of our workflows, we want to have PyIceberg API to do the same. And then we are delivering the same set of deliverables to client. It's just we are optimizing our processes. We are trying to use the best thing, fast thing possible. Yeah, I think, hope that answers the question.
All right, well, that's perfect. We're at the end of time. Again, thank you very much, Ben, Gautami. Fantastic presentation.